this question, I'm going to solve Coletta problem 10.8, which is talking about an athlete who's doing leg curls. We're able to see a picture of the distribution of weights, and she's slowly raising the foot and lowering the leg, and this is the joint, so it's rotating about this origin here. Now, right now she's holding the leg stationary, so we'd like to find the tension in the quadricep tendon, that's right up here, and that's the end of the question in the book, but I'm adding a part just so I can give you more examples of how to do this type of problem. I'm saying let's also find the forces at O from the joint on the lower leg bone. All right, so why don't you see how much of the analysis and planning you can do for this problem? Okay, so my first step is to realize that because this current picture is stationary, this is a static equilibrium problem. So static equilibrium means that the sum of the torques is 0, the sum of the forces in x is 0, and the sum of the forces in y is also 0, right? Because there's no accelerations, nothing's moving at all. This would also be true if everything was going at constant velocity, right? Constant angular velocity, constant velocity in x and y. But usually static equilibrium problems, everything's at rest. So that's what this picture is here. So the next step is to draw a free body diagram of this, clearly showing all the forces and their locations. So here is the pivot point where if things were moving, it would rotate around this point. So this is the joint where the bone's connected. So that's the O right here. And this rectangle is meant to be my representation of the bone. So at the very far end, there's the weight putting a 250 Newton force straight down. And then this other force is the force up here of the quadricep acting at a 53 degree angle above the horizontal, and we also know that it's acting 6 centimeters away from O. So it's looking like, oh, and I forgot to put one thing in my drawing, which is that we know this angle is 60 degrees here. Okay, so where do we go from here? This is looking like a pretty complicated problem with a lot of different things. Well, the first thing would be to figure out our goals. Our first goal is we'd like to figure out the magnitude of this force Q, right? We already know its direction, we'd like to figure out its magnitude. And that's find the tension in the quadricep tendon. So that's what this force is representing, the tension in the quadricep tendon. Okay, and then part B, which I added on, is find the force acting at O from the joint on the lower leg bone. So that would be what force here is acting on the joint, maybe pulling it, pushing it, and it's probably at some angle. That I know nothing about, so I just said it had some x component, some y component, and my goal is to find the x component and the y component of that force and combine them to get the magnitude and direction of that force that's pulling or pushing. And I just guessed directions for these. And later, if it turns out negative, that'll show that my guess was wrong. So I guessed Fy was up and Fx was to the left. I've also put in my XY axis here. And I'm going to choose so given that this is my next step, I need to choose my axis of rotation, right? And here I want to really be strategic because it's best to put my axis of rotation at the location of the most unknowns. So I could have put it right here where I have FQ, but that's sort of one unknown. Here I don't know the X or Y component. So I'm going to put my axis of rotation right there where I have the most unknowns. Now that I have my axis of rotation, if I look at my statics problem-solving strategy, the next thing is to just march through each of these equations. Sum of the torques equals 0, sum of the forces equals 0 in X and in Y. So I think I'll start with the sum of the torques equals 0 equation. Why don't you see if you can execute that equation and see where it gets you? All right, my first thing that I'm doing is the sum of the torques equals 0. So that means 0 equals all the torques added together. The torque from the force of Y and X, the torque from Q, and the torque from the 250 newtons. Now right away, these two are not generating any torque because torque is Fr sine theta, but they're not any distance from the axis of rotation, right? You know if you push a door right at the hinge, it won't rotate. So that's why both of those are 0. Then we have the torque from force Q, which is its force, which we don't know, but remember that's good because it's good to get this variable in here because that's our goal. 0.06 meters, that's the distance it is away from the axis of rotation. And then the angle between that line to the axis of rotation and FQ is 53 degrees, so we put sine 53 degrees. Then we need to get the torque from this 250 newtons. Well, 250 newtons, the force, times the radius is 45 centimeters. And then we have to be careful because what we really want is the angle between this line and the force. And that's not exactly what we've been given. But if we come back up here to this picture, it's even clearer using geometry that 60 degrees, even though it wasn't drawn that way, is actually the angle that we want here. So then I can put in sine 60 degrees. And actually, normally when you do this kind of problem, you would then just keep marching through some of the forces in X, some of the forces in Y to get your unknowns. But this is really good because just doing the sum of the torques, we have an equation and the only unknown in there is our goal. So we can actually just use the sum of the torques equation to get our goal and then move on to part B. Go ahead and see if you can execute that. But before we do that, I realized I was, again, not careful with the sign of my torques, right? So this is a really important thing to think about. The sign of this FQ is positive because it's going counterclockwise, but this 250 newtons is going the opposite direction. So I actually should make this a minus sign right here because this is going clockwise, so this is a negative torque. All right, now let's continue with our execution. All right, and from this step, it was really just algebra to solve for FQ, algebraic rearrangement. And when I plug in, I get 2,033 newtons, or to 2 sig figs, 2,000 newtons. And that is surprisingly large when I look at this picture, right? This person is just lifting a 250 newton weight, and yet they need 2,000 newtons of tension in the quadricep tendon? Does that make sense? So this is a good monitoring step, right, to make sure the answer makes sense. And actually, in problems involving torque, something like this is really common. Because you can see actually the radius here in FR sine theta is really small for the quadricep tendon compared to the weight. The weight's acting out here way out at 45 centimeters, but the quadricep tendon barely has any lever to work with. It only has the 6 centimeters. So therefore, you have to pull a lot harder here to counteract here. It'd be like a seesaw with one really long arm and one really short arm. You know you'd have to put a much heavier person on the shorter arm. All right, so we were able to just use the sum of the torques equals 0 in order to get part A, the force on Q. Now, to get our next goal, part B, the force on X, the force on Y, and really the combination for the magnitude and direction, I'm going to have to move on to the next parts, do the sum of the forces in X is 0 and the sum of the forces in Y is 0. I'll clear up some space here. Why don't you pause and see how much of that execution you can do? All right, let's start with the sum of the forces in X. Before I even got to that point, what I did was I broke up FQ into its components. It has an X component and a Y component. I wrote them here. I noticed that the X component is negative. All right, so sum of the forces in X equals 0 and sum of the forces in Y equals 0 is something that you've already done, right? So you know how to break forces into components. You know how to do X and Y sums. Maybe you haven't done them in this particular context of a static equilibrium problem, but this part now should sort of be review. All right, and looking at this picture, I can already see that I guessed the wrong direction for Fx, right? Like two forces to the left are not going to add to 0. So really Fx better be to the right. And I'm not going to change my guess because I just want to see how it comes out here in the math. So here's my sum of the forces in X equals 0. I have Fx, which at the moment is pointing to the left. And I have Fqx also pointing to the left. Then I have no X component from the 250 newtons. Those all add to 0. Let me solve them for Fx. All right. So here where I have Fx, this is just the magnitude, the length of this line, and the negative is already telling me it's pointing to the left. Here, Fqx is minus 1,223 newtons. Notice that even though I had a minus sign here and here, those were both just telling me it went to the left. So I only kept one of them in here, right? So that this force is going to the left. Then I solve this equation and I get Fx is minus 1,223 newtons. So the fact that there's a minus sign in here is telling me that I made this arrow going the wrong way. And so what Fx really should be is 1,223 newtons to the right. All right, and don't get too concerned about these minus signs because you can usually look at the picture and make a better guess than I did once you get to that stage. All right, so this is great because I've already gotten Fx from my sum of the forces in X equation. Let's see if we can similarly get Fy from my sum of the forces in Y equation. All right, so here my sum of the forces in Y is 0 because I have no Y acceleration. Here's all the sum of the net force in Y, like sum of the forces in Y. That's the force Y here applied at the joint, the thing we're trying to find. Of course, we have FQY, which is going up, and the 250 newtons that's going down. I solve these for Fy with some algebra, and I get a minus 1375 newtons. Oh, so I guess the direction of y wrong too, which actually kind of makes sense because, if I guess the direction of Fy wrong here, which actually kind of makes sense because this Fq is so much bigger than this here that we're going to need a downward force to balance this out. So here, what's actually happening is at this joint, the joint is providing a compressive force to the right and a force downward, and that's what's balancing it and keeping this whole bone stationary so that it's both not rotating, that's the FQ, but also not accelerating. All right, so now we've got Fx, we've got Fy, we want to combine them to give the magnitude and direction. Again, this is something that you've done a lot of times before, just a vector addition. So see if you can use this as a good review to figure out what is F, the force here applied at O, magnitude and direction. All right, here I have the x and y components, and of course, to do vector addition, I draw my triangle, right? X is to the right, add tip to tail with y, which is down, makes an arrow that goes down to the right. Right, I drew that arrow on here, and then what I need to do is find the magnitude and direction. Well, the magnitude, I just use the Pythagorean theorem, and I get 1,800 newtons when I'm careful about my sig figs. And then the tangent of theta is y over x, so theta is the angle whose tangent is 1,373 newtons over 1,223 newtons, or 48 degrees. And then to answer the question, I could have written 1,800 newtons at 48 degrees below the horizontal, or I boxed this answer and just drew it here on the picture. All right, so now you can see overall how a static equilibrium problem goes. It's just like a big puzzle where once you draw the picture, you do sum of the torques equals 0, sum of the forces in x equals 0, and sum of the forces of y equals 0. And in each of those stages, you'll be able to solve for new unknowns. All right, we're done with this example.